Welcome back to this next video in which we are discussing finite dimensional vector spaces. Okay, so in the previous video what we saw was the definition of a finite dimensional vector space. Okay, what I now want to prove then is that whenever a vector space is finite dimensional, that there will always exist a basis for that finite dimensional vector space. And in fact what we will see is exactly how we can construct a basis for that finite dimensional vector space. Okay, right. So how are we going to do this? Well, the absolute starting point is the definition of finite dimensional vector space. Okay, so remember, a finite dimensional vector space is one for which there is a finite subset of vectors of that vector space which spans the entire vector space. Okay, so that is the set of vectors that we are going to start off with if we're going to try and construct a basis, because remember, a basis, one of the conditions is that it needs to span the entire vector space. So the natural place to start is with this set of vectors that we are given, which spans the vector space. Okay, so because we're working in a finite dimensional vector space, there will exist some subset, some finite subset of the vector space. Okay, so I'll draw it again here. So we've got this finite set of vectors from the vector space, v1, v2, all the way up to vn here, which spans the entire vector space. So all vectors in the vector space can be written as a linear combination of the vectors in this set. Okay, and we're going to use this to construct a basis, and we know that this exists because that's the definition of a finite dimensional vector space. Okay, so I'll just write the fact that span of S is equal to the entire vector space. Okay, right. So either this set of vectors is linearly independent or it is not. If it is linearly independent, then we're done. We have a basis, okay, because we have a set of vectors which spans the entire vector space and which is linearly independent, and that's the definition of a basis. So we're done if this set of vectors is linearly independent. The problem is, what if it's not linearly independent? Then what are we going to do? Okay, well, if it is not linearly independent, what does that then mean? Well, that means that there must exist a non-trivial linear combination of these n vectors which gives the zero vector. Okay, so I'll just write that down. So what's going to exist then is there's going to be a non-trivial linear combination. So I'll write this non-trivial linear combination here, c1 v1 plus c2 v2 plus all the way up to cn vn, which is equal to the zero vector. Okay, where not all of these coefficients here, not all of the ci's are actually going to be zero now. Some of them, at least some of them, are going to be non-zero, so that this is a non-trivial linear combination of these n vectors which gives the zero vector. Okay, now, what I show in the video on linear independence is that as soon as it's true that the set of vectors is not linearly independent, i.e. instead it is linearly dependent, that what it's possible to do is write one of the vectors in the set as a linear combination of the others. Because that is so foundational to this proof, I'm going to repeat the argument of that here. Okay, so let's go over this. So what I want to do then is prove that if we have a non-trivial linear combination of these n vectors which gives the zero vector, that I can write one of these vectors in this set as a linear combination of the others. And then what we're going to do is show that if you remove that vector which you can write as a linear combination of the others from the set, then the set will still span the entire vector space. Okay, and that's going to be the basis for our proof that we can continue reducing down our set until we end up with a linearly independent set. Okay, right. So let's firstly see then why it's the case that if I have a non-trivial linear combination of these n vectors which gives the zero vector, that I can write one of these vectors as a linear combination of the others. Okay, so what I've said is that at least one of these coefficients here must be non-zero, okay, in order for this to be a non-trivial linear combination which gives the zero vector. Okay, so let's say, for argument's sake, that it is this coefficient here, Cn in front of Vn. Let's say that this one is non-zero. Okay, so what I can now do is I can take all of these other scalar multiples of vectors in the set onto the other side by adding their additive inverses onto both sides. Okay, so what I'll end up with is the fact that Cn times Vn, so this scalar multiple of the vector Vn, is equal to the additive inverse of all the others added together. So we'll have the additive inverse of C1 times V1 plus the additive inverse of C2 times V2, and it will continue on plus dot 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 all the way down until we'll have the additive inverse of Cn minus 1 times Vn minus 1, like so. Okay, so all I've done there is add onto both sides of the equation the additive inverse of all of these scalar multiples of the vectors here. Okay, now, an important fact then about vector spaces is that if you have the additive inverse of something of this form, a scalar multiple of the vector v, then that is actually equal to the additive inverse of the scalar c in the vector space times the vector v, where this is scalar multiplication here. Again, the first thing I want to do is just give you the proof of that, the very simple proof of this fact. Okay, so firstly let me show you that the two sides here mean different things. Okay, so I want to impose firstly on you how it's not trivial that these two things are actually going to be equal to each other. It's only going to be true because of the beautiful axioms that we insist are going to be true about vector spaces. Okay, so on this side what we are doing is we're firstly scalar multiplying this vector v by this scalar c from the field. We're getting some new vector in the vector space, and we're then taking the additive inverse of that in the vector space. Here, what we're doing is taking the additive inverse of the scalar c in the field, okay, and then we're saying, okay, take that answer and scalar multiply that by the vector v to get some vector, and I'm insisting that these two things are going to be the same thing if the axioms of vector spaces are going to be true. So how am I going to prove that? Well, if I want to prove that negative c times v is equal to the additive inverse of c times v, then all I need to prove is that c times v plus negative c times v is actually equal to the zero vector, because that's exactly what it means to be the additive inverse of cv. It means that you add to cv to give the zero vector. So if I can prove that this is true, then I'm done. Okay, so how am I going to prove that that is true? Well, what I can now apply is distributivity here, so I can factor out the vector v, because scalar multiplication obeys the beautiful distributive property that if you have two elements of the field, and I'll just put this up here and make sure it's in view. Okay, so if I have two elements of the field, C1 and C2, and I add them together and then use that answer to scalar multiply the vector v, it's the same as if I firstly scalar multiply the vector v by C1 and then add it in the vector space to the vector v scalar multiplied by C2. Now understand what a beautiful law that is to be true, because this is addition in the field, okay, almost slipped there, and then this is addition in the vector space. Okay, so this is really saying that you can either add these two scalars together in the field and then multiply the answer by the vector v through scalar multiplication, or you can firstly scalar multiply both of these two elements of the field with their vectors and add them together then in the vector space. It doesn't matter. Okay, and we say that scalar multiplication distributes over addition in the field. Okay, so what we're going to do is use that rule in reverse here. So we're going to factor out that vector v. So we've got a scalar multiple of the vector v added to another scalar multiple of the vector v in the vector space. We're going to change this into c plus negative c, where these two are being added in the field here, times the vector v. So colouring in again here, this is addition in the vector space. We've turned it now into addition in the field here. Now, by definition, c plus the additive inverse of c in the field is of course going to equal the additive identity in the field. It's going to equal 0 just by definition. This was the additive identity, sorry, the additive inverse of c in the field. Now when we multiply the additive identity of the field by any vector, we end up with the 0 vector. So 0 times any vector will give the 0 vector, and therefore we have proven that this thing is indeed equal to the 0 vector, and therefore that negative c times v is indeed negative c times v. Okay, right. So that helps us here, because then what we can do is say that the additive inverse of C1 times V1 is actually just the additive inverse of C1 scalar multiplied by V1. So now what I can do is write this as Cn times Vn is equal to negative C1 times V1 plus negative C2 times V2 plus all the way up to negative Cn minus 1 times Vn minus 1, like so. Okay? Right, so what's my next move going to be? Well, I'm almost there. I now have my vector Vn, well, not quite. I have the scalar multiple of Vn by Cn written as a linear combination of my other n minus 1 vectors, but I want the vector Vn written as a linear combination of my other n minus 1 vectors. So I need to somehow get rid of Cn here. So how am I going to do that? Well, I'm going to scalar multiply both sides of this equation. Okay, now what am I going to scalar multiply them by? Well, this should be pretty intuitive. I'm going to scalar multiply them by the multiplicative inverse of Cn in the field. Now that will always exist because field algebras are incredibly beautiful. Okay, they have multiplicative inverses for all elements other than the additive identity, other than 0. Okay, now we assumed right at the start that Cn was a non-zero scalar. Okay, that's how we chose this one, remember. We said it was non-zero, and we said there must exist one that's non-zero at least, otherwise this would just be the trivial linear combination. Let's, for sake of argument, say that it's this one. Okay, so that's why I know that there will exist multiplicative inverse for Cn in the field, okay, and we are going to now scalar multiply both sides of this equation by this multiplicative inverse for Cn, and it's going to work out very nice. Okay, so if this equation is true, then I can scalar multiply both sides, and the new thing that I end up with will still be true. Okay, so going on to the next page then. So now let's scalar multiply both sides by 1 over Cn, and the first thing, let me just make sure it's straight. Okay, so the left hand side then will become 1 over Cn times Cn times Vn. Okay, so I've just multiplied the left hand side by the multiplicative inverse of Cn in the field, and then on the right hand side I'll end up with 1 times Cn times this great big monstrosity, so negative C1 times V1 plus negative C2 times V2 plus all the way up until we have negative Cn minus 1 times Vn minus 1, like so. Okay, so let's add a bit of colour onto this. Okay, so here's our left hand side, and now here is our right hand side. So all I have literally done is added a 1 over Cn onto both sides. So nothing particularly fancy yet. Okay, let's firstly take on the left hand side here, because this is simpler. So what we're going to do now is apply associativity of scalar multiplication with field multiplication. So what we have here is the vector Vn, firstly scalar multiplied by one element of the field, Cn here, and then scalar multiplied by another element of the field. Now when you've got something of this form, one of the axioms that we insist that scalar multiplication obeys in the definition of a vector space is that you can reassociate this. You can put the bracket around these two things. So you can say that this is the same as 1 over Cn multiplied by Cn in the field, okay, and then take that answer and scalar multiply it by Vn. So you can change the position of the brackets basically, and this is called associativity of scalar multiplication with field multiplication. Now understand how non-trivial that is. Again, this is a very beautiful property that we insist that vector spaces obey, okay, so that they're interesting to study. Okay, because this has turned scalar multiplication into field multiplication. This said, firstly scalar multiply Vn by this, and then take the answer, which is another vector, and scalar multiply it by this. This now says, multiply these two together in the field, okay, so that is a field multiplication there. Okay, take the answer in the field, so this is an answer in the field, and then use that to scalar multiply Vn. Okay, and that's one of the axioms that we insist is true for scalar multiplication. Okay, right. Now, of course this is very nice because, by definition, this is the multiplicative inverse of this. So when I multiply those two together in the field, by definition, I will get the multiplicative identity, 1. Okay, and we know that another one of the axioms that we insist scalar multiplication obeys is that the multiplicative identity of the field, scalar multiplies with any vector in the vector space to just give that vector back again. So that means that we've turned the left-hand side here into Vn, which is intuitively what we wanted to turn it into. Okay, and what multiplying by 1 over Cn should intuitively do. Okay, so that's just the rigorous argument as to why the intuitive thing to happen actually does happen. Okay, so the left-hand side now is equal to Vn. What are we going to do about the right-hand side? Well, firstly, what we're going to do is apply distributivity. So we're going to apply another distributive law that scalar multiplication obeys. Okay, so what we can do is just distribute this out and rewrite this like so. So we'll rewrite it as 1 over Cn times this thing. Okay, so negative C1 times V1, and then it'll be plus 1 over Cn times negative C2 times V2, and then all the way up till you finally have plus 1 over Cn times negative, oops, and I've missed one of the brackets that I want there out, times negative Cn minus 1, oh dear, how am I going to fit this in, times Vn minus 1 there. Okay, nightmare. Right, okay, so we're just using another one of the properties that scalar multiplication obeys, one of the distributive properties that it obeys there. Okay, again, it's a very intuitive property. Okay, it's just working in the beautiful way. Okay, right, so now we've got that, and what we're now going to apply is, of course, the same thing that we applied here, the same trick that we applied here, associativity. Okay, because what we've got is a vector being multiplied by one scalar, get a new answer which is a vector, and then multiply it by another scalar. So of course what we can now do is apply associativity of scalar multiplication with field multiplication and say, let's rewrite this as multiply 1 over Cn, the multiplicative inverse of Cn, by negative C1 in the field, and then take that answer in the field and scalar multiply it by V1, add that to 1 over Cn times negative C2 in the field, and scalar multiply that by V2, and continue on, plus all the way up until we'll get 1 over Cn times negative Cn minus 1 times Vn minus 1 in the field, like so. Okay, so we've just applied associativity, and all of these things that we've got here, these are just elements of the field being multiplied in the field to get other elements of the field. So all of these are just elements of the field, capital F. So this is an element of the field, this is an element of the field, all the way up to this n minus 1th, which is an element of the field. Okay, so we have now succeeded then in writing Vn here as a linear combination of the other n minus 1 vectors, because all of these things that I'm multiplying my vectors by are just elements of the field, so it is now just a linear combination. Now, we're going to need this linear combination, but at the moment it's written out hideously, okay, because these things are a big effort to write out, and if you leave them like this, where we're going, what we're about to do, it just becomes too much like hard work to have to write this continuously. So I'm going to change my notation now to make it slightly easier on the writing out, okay, and make it look slightly simpler. So I'm going to rename these coefficients that we've got here, okay. All I'm doing is renaming them. So I'm going to rename them as the a's. So I'm going to write Vn is equal to a1 times v1 plus a2 times v2 plus all the way up to an minus 1 times Vn minus 1. Okay, so Vn is written as a linear combination of the vectors v1 to Vn minus 1. So all of these ai's are elements of the field. Okay, so all I've done is rename these scalar coefficients in the linear combination, which is something that I have perfect privilege to do, okay, and which is going to just make it easier on the eye what we're about to do. Okay, so the important message there is that if this set of vectors, capital S, and I'll just get our set of vectors back up here, if this set of vectors is not linearly independent, then you can write one of them as a linear combination of the other ones. Okay, now, the big claim now is that I can take this vector Vn out of the set. So I can create a new set, which is S prime, which will contain all of the vectors of S bar Vn. So it will go all the way up to Vn minus 1 rather than Vn, so no Vn is in this set. Okay, and my claim is that this set, S prime, will still span the entire vector space. Okay, so I claim that we don't need this vector in the set in order for the set of vectors to span the entire vector space. So my claim, and this isn't proven yet, but we're about to prove it, is that span of S prime is still equal to the entire vector space. Okay, so I claim we haven't lost any span by removing the vector Vn from the set. Okay, so how am I going to prove this then? Well, the way I'm going to prove it is consider an arbitrary vector in the vector space. Okay, now, so if I'll take an arbitrary vector in the vector space, which I'll call little v, so this is just some arbitrary vector in the vector space. Now, previously, the set capital S, by assumption, it was the set that spans the entire vector space, okay, which we knew we could find if our vector space was a finite dimensional vector space. Okay, so I could write little v as a linear combination of those vectors. Okay, so what symbol shall I use? I'll use b's. Okay, so I could write v as b1 times v1 plus b2 times v2 plus all the way up until bn times vn, where again these bi's are elements of the field capital F. Okay, so that's just applying the fact that the set capital S spans the entire vector space. So I could write this arbitrary little vector as some linear combination of the vectors v1 all the way up to vn. What I now want to do is prove that I can write this arbitrary vector little v as a linear combination of these ones, i.e. I don't need the vn. Now how am I going to do this? Well, hopefully this should be pretty intuitive. I'm going to substitute in the fact that I can write Vn as a linear combination of the other n-1 vectors, so I'm going to stick this in here and then hope that I can rearrange it then into a linear combination of the other n-1 vectors. And since this was an arbitrary vector in the vector space, then the argument will apply for them all. Hence, this set S prime will span the entire vector space. Any vector in the vector space will be writable as a linear combination of those vectors v1 and v2 all the way up to vn minus 1. So let's do this, and this is why I changed the notation so that I don't have to write this hideous thing in. Instead I can write this thing in. Okay, so my vector little v then, firstly let's have the b portion, so we'll have b1 v1 plus b2 v2 plus all the way up to bn minus 1 vn minus 1, and then something interesting will have happened up here, plus bn times, and now I'm going to put in for vn this thing here. So I'll now have a1 times v1 plus a2 times v2 plus all the way up to an minus 1 vn minus 1 there. I'm sorry, it gets smaller and smaller as it goes along. Okay, so that's perfectly valid to do. Okay, now what I want to do is just rearrange this, as we know we will be able to do, but we will go through the rigorous arguments as to why, into a linear combination in the vectors v1, v2 all the way up to vn minus 1. Okay, so the first thing to do then is apply distributivity to here. Now we've done this before. Okay, so we're going to multiply out the bn, okay, and split it up into the different portions. Then what we're going to do is apply associativity. So I'm going to try and do two steps in one here. So I'm going to first apply distributivity, and then I'm going to apply associativity. I'm effectively going to do the exact same thing that we did here. We applied distributivity, splitting it into this, and then we applied associativity, splitting it into this, but this time I'm going to do it all in one step to save some time, since we've already been through those arguments already in this video. Okay, so our vector little v will be b1 v1 plus b2 v2 plus all the way up to bn minus 1 times vn minus 1, and then what we'll end up with is plus bn times a1 in the field, that's a field multiplication there, scalar multiplied by v1, so I'll emphasize this, these two are multiplied together in the field, so I've applied distributivity and then associativity to turn it into this. Then I'll have plus bn times a2, again multiplied in the field, and then scalar multiplied by v2, like so, and then it will continue on plus dot 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 all the way up until we finally end up with bn times an minus 1, like so. So these two are multiplied again in the field, and then scalar multiply that by vn minus 1 here. Okay, right, so that's perfectly valid to do. Now all I want to do is get this portion together with this portion together with this portion, and so on, this portion together with this portion. So firstly, what I'm going to do is just apply associativity and commutativity of addition to move this around. So addition obeys these two beautiful properties of associativity and commutativity. So addition of vectors we're talking about here, because it's an abelian group, it has associativity and commutativity. Associativity tells us it really doesn't matter where the brackets are in addition, which is why I haven't bothered putting any brackets in, because it really does not matter where you put them. And commutativity tells us that it doesn't actually matter what order the vectors appear in this great big sum. Okay, so what I can do is freely move these around. So what I'm going to now do is bring this one and this one next to each other. So v is going to be equal to b1 times v1 plus this thing over here. So plus bn times a1 times v1, like so. So I brought the two things that contain a vector v1 close to each other. Then what I'll do is the same for the vector v2. So then I'll have plus, and then we'll have b2 v2 from here, and then plus this portion from over here. So then I'll have plus bn times a2 times v2, like so. I'll just move this up a bit. So we'll underline all of those ones referring to v2 in green here, and then we'll continue doing this for v3, v4, etc., all the way down to vn minus 1, and we'll end up with plus bn minus 1 vn minus 1 plus, and then this portion, bn an minus 1 times vn minus 1. Okay, like so. And now what we're going to do is we're going to factorize out the vectors. So we're going to factorize out v1 from here, we're going to factor out v2 from here, we're going to factor out vn minus 1 from here, using one of the distributive laws that scalar multiplication must obey. Okay, the second of the two distributive laws, which we did indeed use earlier to prove this fact here. So here it is stated here, the second of the two distributive laws that we insist scalar multiplication must obey, and we used it to prove that negative c times v is equal to negative c times v. Okay, right. Let's now factor out v1, v2, vn minus 1, etc. So that will then mean that the vector v is equal to b1 plus bn times a1 times v1. Okay, now all of these things here, this is addition in the field, this is multiplication in the field, so all of this is just field operations. We are taking a few elements of the field and we're adding and multiplying them in the field, and we'll end up with some other element of the field is the important thing there. Okay, and likewise for all the rest. So for v2 we'll have b2 plus bn times a2, and then all of that again is done in the field, and then the answer to all of this, which is an operation in the field, scalar multiplied by v2. Okay, like so, and then you'll continue this process on, and you'll go all the way on until the final one down here, where we have bn minus 1 plus bn times an minus 1 times vn minus 1, like so. Okay, where again this is multiplication in the field and this is addition in the field, so this is just some answer in the field. And hence, what have we done then? We have written our vector, little v here, as a linear combination of the vectors v1, v2, all the way up to vn minus 1, because all of these elements that I have underlined in orange, these are just elements of the field. We are just adding together loads of things which were elements of the field, multiplying things that were elements of the field, and overall, well, what we end up with is something that's in the field. Okay, so I'll just stress that this is an element of the field, this is an element of the field, and this final thing over here is an element of the field. Okay, so this is a linear combination of the vectors v1, v2, all the way up to vn minus 1. So what I've proven now is an arbitrary vector in the vector space can be written as a linear combination of the remaining n minus 1 vectors, and therefore indeed this reduced set S prime does indeed span the entire vector space, capital V. Okay, right. So, how now does this work? So what were we actually trying to do? It's probably a good time to sort of remind ourselves of what we were actually trying to do with this proof. we were trying to prove that you could always construct a basis for a finite dimensional vector space. And we started off by saying, okay, because it's a finite dimensional vector space, there exists this set, capital S, which is a finite set of vectors such that it spans the entire vector space. Okay, now we said either it's linearly independent, in which case we've got a basis, bravo, or it's not linearly independent. And then what we can do is we can remove one of those vectors Vn from it, okay, and we will end up with a smaller set of vectors which still spans the entire vector space. So if it isn't linearly independent, you can remove a vector and it will still span the entire vector space. Okay, that's what we've just proven. So here now goes the proof. Okay, this new set that I've got here, S prime, either it will be linearly independent or it will not be. If it is linearly independent, then it is a set of vectors which is linearly independent and which spans the entire vector space, so now you've got a basis. If it is not linearly independent, then the exact same argument applies again. What you can do is say one of these vectors must be writable as a linear combination of all the others, remove that one, okay, so you'll get a smaller set. And you can continue on this process. You can continue on taking vectors out of the vector space for as long as the smaller set is still not linearly independent. And what we've shown is that you can always remove one of these vectors from this non-linearly independent set, and the span will not be affected. Okay, so removing this vector had no effect on the span. Okay, so you can do this again. If this isn't linearly independent, remove another one, and it won't affect the span. Okay, so you can continue on making the set smaller and smaller and smaller and not decreasing the span of the set until you end up with a linearly independent set. Okay, now there is the possibility that you continue on taking down the elements of this set until you end up with only one element. Now, obviously sometimes you'll continue taking it down and eventually you might have a set, let's say, of 5 elements, and then finally you get a set that is linearly independent. It still spans the entire vector space, so you've found a basis. Okay, but there is the possibility that you continue on going down all the way until you end up with a set that just contains a single vector. Okay, so let's say we have done this process and we've got to a set now that contains a single vector. Okay, so is this now the basis? Okay, so remember the way that this proof has gone is that it will still be the case that the span of this entire set is the entire vector space, because remember, whenever we've been removing elements, we haven't been changing the span. So the span of this set is the entire vector space. The question is this always now going to be linearly independent? Is it the case that if you do end up reducing your set down to a set that just contains one element, that you end up with that being the basis? Okay, because we're trying, remember, to prove that this always works, that you'll always eventually end up with a set that is linearly independent. So we've now got to address the possibility that you do end up with a set that just contains one element. Okay, so this will always be linearly independent providing this vector is not the zero vector. Okay, and the reason that a set that contains a single vector will always be linearly independent, providing this vector isn't the zero vector, is because if you consider the linear combinations of a set that contains only one vector, then all it is all the scalar multiples of that vector. Now, the definition of linear independence then says that the only way that a scalar multiple of this vector can equal the zero vector is if this scalar is equal to 0. Okay, so if this set is going to be linearly independent, it must be the case that the only solution to this equation is where this element C here is equal to 0. Okay, now there is one case where that won't be true, which is when the vector here, the only vector that you've got left in there, is the 0 vector. Now, if this vector was the 0 vector in your set, capital S, then whatever scalar you put here and scalar multiply the 0 vector by, you will end up with the 0 vector. So the set that contains just the 0 vector is not linearly independent. But all the other sets containing just a single vector, okay, where this vector is not the 0 vector, they will be linearly independent, because for any non-zero vector, scalar multiple, the only scalar multiple of that non-zero vector that will give you the 0 vector will be the case where this has to be 0. Okay, and I'll just prove that result for you. Okay, so I'll get another piece of paper here, and we'll just try and prove that result, because it is quite important. Okay, so what I'm trying to prove then is that the set containing just one vector will be linearly independent if it is not the zero vector. So we are assuming now that V is some element of a vector space that is not the zero vector. Okay, and what we want to prove is that if you multiply it by any scalar except 0, you will not end up with the zero vector. So let's say C is an element of the field that is not the zero vector. Okay, like so. Right, so what we now want to prove is that C times this vector is not equal to the zero vector. Okay, now the way we're going to do that is proof by contradiction. Okay, we're going to assume that it is true that we can multiply our non-zero vector by a non-zero scalar and get the zero vector, and we'll arrive at a contradiction. Okay, so let's assume that CV is equal to 0 for some element of the field that is not 0. Okay, then what can I do? Well, if this equation is true, I can scalar multiply both sides of this equation by some element of the field, and it will still be true. Okay, so the element of the field that I'm going to scalar multiply both sides by is the multiplicative inverse of C. Okay, like so. And the reason I can do that is that C, by assumption, was not 0 in the field. So the multiplicative inverse of C will always exist. Okay? Now, on this side, I am multiplying some element of the field by the zero vector. We know that whenever you multiply any element of the field by the zero vector, you get the zero vector back again. So that side's easy. That's going to be the zero vector. This side is more interesting, because what you can now do is apply associativity and say that this is 1 over C times C in the field, scalar multiplied by V. But 1 over C times C in the field, that's going to equal the multiplicative identity of the field. This is going to equal 1. 1 times V is just equal to V, so we then end up with the equation that the vector V had to be the zero vector. Okay, but we assumed that V was not the zero vector. Okay, so what I have overall just proven to you is that the only way you can multiply a non-zero vector by some scalar and get the zero vector is if that scalar was 0 in the field. Okay, and that then proves that this set just containing a single vector where this vector is not the zero vector is linearly independent, because the only linear combination of it that will give the zero vector is the trivial one where the scalar is 0. Right, so what I've proven then is that if you do end up with a set that contains just one vector, providing that vector is not the zero vector, it will be linearly independent. We know that the set spans the entire vector space because whenever you've taken vectors out, you haven't reduced the span, so you will then have a basis. You will have a linearly independent set of vectors which spans the entire vector space. So you will have constructed a basis. There's one final hole, okay, that needs filling. What if the final vector that you reduce your set to is the zero vector? Okay, well, let's just think about this. Okay, this isn't linearly independent is the problem that we're facing. But let's think about what it actually means. We said that this set had to span the entire vector space. Okay, what is the span of a set that contains only the zero vector? Well, that will be all scalar multiples of the zero vector, but all scalar multiples of the zero vector are the zero vector. Multiply the zero vector by any scalar you want. In a vector space, you'll get the zero vector back again. Okay, so that means that the entire vector space we were working with only contained a single element, i.e. the instant that this set that you end up with just contains the zero vector, it tells us that we were working with a very silly vector space, basically. It tells us that we were working with the zero vector space, the vector space that only has a single element. Okay, so I'll just remind you of what the zero vector space actually is. So the zero vector space is a very silly vector space. It can be over any field you like, so pick whatever field you like. A ridiculously complicated field, potentially. You can pick the real numbers, the complex numbers, whatever you want. Okay, it is the vector space that only contains a single symbol. Okay, and we'll call that symbol 0, but you could use any symbol you like. Okay, so here's the actual set that underlies the zero vector space. The addition law is very, very simple. So the addition law, the only possible addition that you've got is 0 plus 0, and the only answer you can get is 0. Okay, therefore it is the additive identity in this vector space, trivially. And then finally, we'll have scalar multiplication. The only vector is the zero vector, so we'll only have one column. We potentially have an uncountably infinite set of field elements down here, so the field could end up being horrendously complicated, but of course all the elements of the field are just going to multiply by the zero vector to give the zero vector. Okay, so all of the answers here are just going to be 0, 0, 0, 0, 0, 0, 0, 0, potentially an uncountably infinite column of zeros here, but the point is it's just a column of zeros. Okay, now, stupidly, this structure does obey the axioms of a vector space. Okay, and it's called the zero vector space over the field F. Okay, so, basically, if you were if you had one of these sets and you were trying to construct a basis and you ended up reducing your set down to the set that just contains the zero vector, then that instantly tells you that the vector space you were working over was some zero vector space over some field capital F. Okay, this is not a basis because although it spans the entire vector space, it's not linearly independent. Okay, because any scalar multiple of 0 is equal to 0. Okay, so it's not the case that there's only one linear combination which gives the zero vector. So, what is the solution here? Okay, well, we use what we defined in the previous video in this playlist on vector spaces on the basis of a vector space. Okay, we said in that video that we would define the empty set to be the basis of the zero vector space, and this is one of the reasons why. Okay, even though this seems a stupid thing to do initially, because how on earth does the empty set span anything? How does it create, what linear combination of vectors in the empty set gives the zero vector? Okay, so it doesn't intuitively feel right that this would span the zero vector space, but here is the reason that it's a good idea to define that as the basis of the zero vector space, because in the proof that we've just gone through, it now means that we don't need to view this as a special case, okay? Because what we can now do is just say, okay, this isn't linearly independent, therefore remove the final vector from here, end up with the empty set. The empty set, by definition, is linearly independent, and it also, by definition, spans the zero vector space. So we're just going to define it to be the basis of the zero vector space over any field capital F, and therefore we have arrived at a basis. So this is one of the great arguments for why you define the basis of the zero vector space to be the empty set, because then this proof works for all of them. Okay, you can always take a set that spans the vector space and reduce it down, gradually take elements out when the set isn't linearly independent and not affect the span, and then end up eventually with a basis, and you don't need to view the zero vector space as a special case. This approach still works because of all you'll end up doing is reducing down to the empty set, and then the empty set is a basis of the zero vector space by definition. Okay, so I hope that hasn't confused you, okay? It is a bit silly, but that finishes the final hole in the proof that you would otherwise have with the potential for ending up with the zero vector being your final vector in that set of one vector. Okay, so what I have now proven then is that all finite dimensional vector spaces have a basis. Okay, it is always possible to construct a basis. You can take the set that spans the vector space, the finite set of vectors which spans the vector space, which by definition has to exist, and you can gradually go about reducing the size of that if it's not linearly independent. You can always reduce the size of it, take a vector out, and it won't affect the span of that set of vectors, okay? And then you just continue on until you end up with a linearly independent set. And either you eventually hit a point where you do have a linearly independent set, or you end up with a set that contains just one vector that will be linearly independent unless it contains the zero vector. But if it does contain the zero vector, and that's the only vector that's left in it, then that must mean that the vector space we're dealing with was a stupid vector space. It was the zero vector space, so just go ahead, take the final one out, end up with the empty set, and we'll just define that to be the basis of the zero vector space. Okay, so we'll have a break there, and in the next video what we'll do is we'll tackle the main theorem of this video, which is that the number of elements in any basis of a finite dimensional vector space is going to be the same. So if you have a vector space and you have two bases of that vector space, they'll have the same number of elements in, which is a very intuitive theorem, okay, but it needs proving.